It's funny. Sometimes the biggest, most profound ideas start with the simplest little questions. Today, we're going to follow the thread of one of those questions. It starts with a sharp student noticing something odd in a statistics formula, and it ends with a totally new, powerful way to look at uncertainty and risk itself. It's quite a journey.
And it all began right here, with this question on Reddit. A student, Mikey Likes It 123, was staring at two probability formulas, and something just felt off. And honestly, this is a fantastic question. It's the kind of question that cuts right to the core of what our mathematical models are really assuming about the world.
So this isn't just about, getting the right answer for homework. This is about the story that each of these statistical models is telling. It's about these really subtle, but absolutely crucial differences in the worlds that they're trying to describe.
Okay, so here's where the confusion comes in. If you look at the hypergeometric formula, it has a part that counts all the ways to arrange successes and all the ways to arrange failures. But the binomial formula, well, it seems like it only cares about the successes. It looks like a whole chunk of the formula is just gone. So is the textbook wrong? Or is there something deeper happening here?
Well, luckily, a statistics tutor jumped into the Reddit thread with a perfect explanation. It turns out, the answer to this puzzle isn't really hidden in the math itself. It's in the scenario the math is built for, and it all boils down to one key difference.
And this lays it out perfectly. On the left, you've got the binomial distribution. Think of this like drawing a marble from a bag, and then you put it back. Every single time you draw, the odds are exactly the same. The population is basically infinite. Now, on the right, you've got the hypergeometric distribution. This is like drawing a marble and not putting it back. Every draw changes the odds for the next one, because you're dealing with a finite known group of marbles.
And that's the aha moment. See, the binomial formula doesn't need to count the failures, because once you've decided where your successes go in a sequence of tries, the failures just have to fill in the empty spots. Their places are already locked in. The hypergeometric formula has to count both because it's like grabbing a whole handful of marbles from the bag all at once. Different assumptions mean you need different formulas. Puzzle solved.
And this is where our story takes a really fascinating turn. Because, okay, answering the student's question is one thing, but it cracks open a much bigger, much more important question for all of us. If we have different models, different forecasts, all trying to predict what's going to happen, how do we know which one is any good? How do we actually grade them?
So now we're moving out of the textbook and into the real world, where we have to evaluate complex forecasts. And this is where statistics becomes an incredibly powerful tool. But we're going to need some more advanced gear to do it. Let me give you an analogy. It's pretty easy to think about a simple forecast, right? Like a 50% chance of rain. But what about a modern weather forecast that predicts multiple things all at once? The wind, the temperature, the humidity, the rain, all together. How on earth do you give a single grade to a forecast that complex? How do you score it? Well, the pros tackle this with something called a scoring rule. You can think of it like a really detailed report card for a forecast. It checks two big things. First, is the forecast calibrated? Meaning, on average, is it statistically consistent? And second, is it sharp? Meaning, was it confident and precise? A really good scoring rule has to get the balance between those two things just right.
And the real beauty of a scoring rule is its simplicity. It takes all of that complexity, all this talk about sharpness and calibration, and it boils it all down to a single number. And with that number, we can directly compare two different models and say this one's better. In this case, the lower the score, the better the forecast.
Okay, so the researchers behind the paper we're looking at came up with just a brilliant way to think about this whole problem. To figure out how to score a complex forecast, they first figured out a new way to see it. Check this out. Instead of picturing a probability distribution like a big hill, the researchers imagined it as a topographic map. You see those rings? Each one of those is what's called a level set. It's a zone where the probability of something happening is exactly the same. It's an incredible way to slice up all that uncertainty into these clear, measurable regions. Okay, so we've got our forecast, our probability map. Then something actually happens in the real world. We get a real observation, let's call it Y, and it lands somewhere on that map. So how does the scoring rule use that one little dot to grade the entire map?
Well, here's how it works. If the actual outcome, Y, lands inside one of your predicted regions, your forecast gets a good score. The rule basically rewards you for being accurate and precise, for making your prediction region as small as possible while still managing to capture what really happened.
But if the outcome Y lands outside your predicted region, the forecast gets penalized. And here's the really clever part. It's not just a simple "you were wrong." The score actually measures the distance from your prediction to what really happened, giving you a very precise grade on exactly how wrong you were. So here's a great comparison. On the left, we've got the map of reality, the true distribution. And on the right, we have a forecast that's a little bit off. It didn't quite get the relationship between the two variables right, so its shape is a little squashed. Now, to our eyes, they might look kind of similar, but a good scoring rule is designed to spot that subtle difference and put a number on it.
And it does. In the simulation they ran, the true distribution got a score of negative 18,635. This flawed forecast, it got a score of negative 15,174. And since a lower score is better, the score correctly tells us that the forecast on the right is worse. It has successfully put a number on just how wrong that model is. I mean, that is just incredibly powerful.
So as you can probably guess, this is way more than just a cool theoretical exercise. These tools for grading complex forecasts have massive, massive real-world applications in fields where understanding risk is, well, everything.
And I mean, just look at this list. We're talking about finance, where this helps manage huge systemic risks. In environmental science, it's used to figure out the combined risk of things like storm surge and wave height to protect our coastlines. In hydrology, it helps assess flood danger. And in data science, it helps build better systems for spotting weird anomalies. In every one of these fields, knowing how good your forecast is can have enormous consequences.
It is just amazing to think that this entire journey, all of this, started with that one simple curious question on Reddit about a missing piece of a formula.
And from that one question, we've unraveled this whole sophisticated framework that lets us see, score, and ultimately get better at predicting things in deeply complex systems, from our climate to our financial markets.
And that really is the whole leap, isn't it? It's the journey we all take from being a student to being a practitioner. It's not just about asking if the math is correct, it's about asking if the model is actually useful for understanding the world.
So we've seen how one person's curiosity can connect a simple textbook problem all the way to the cutting edge of risk analysis. It just goes to show the biggest breakthroughs often start when someone is just brave enough to ask a simple question. So what are you going to be curious about?